In this video, we describe the GASP algorithm for visualizing Reeb graphs. The Reeb graph is a compact structural abstraction of a function defined on a manifold. For faithful visualization of the scalar function, a Reeb graph should possess some essential properties. First, because the scalar field is defined on the manifold, Reeb graph arcs should remain confined within it. Any arc that exits the manifold implies the Reeb graph exists outside the manifold. Second, the Reeb graph arcs should be as short as possible to minimize visual clutter and facilitate easier interpretation. Third, arcs should follow the function gradient so that the Reeb graph reflects how the scalar field changes. In this example, the function is horizontal, but the arcs in red move both vertically and horizontally, which obscures the true pattern. Existing algorithms for drawing Reeb graphs are agnostic to, or violate these properties. To address this, we introduced the GASP algorithm. Now, we will describe the GASP algorithm using a torus example. GASP starts by decomposing the model into topological cylinders. 1. Per Reeb graph arc. The torus is divided into 4 topological cylinders because of its 4 Reeb graph arcs. After decomposing the model into topological cylinders, GASP then extracts isocontours on each cylinder. The space between 2 consecutive contours is a user set parameter, which the user can increase or decrease. After extracting the isocontours, GASP then calculates candidate points from the extracted isocontours. Candidate points can be either from the contour for the boundary approach, or inside the contour for the interior approach. With the candidate points on each isocontour, a path graph is formed between the candidate points of consecutive contours and between the critical points on the first and last isocontours. Among all the paths, only the shortest path is extracted as the potential Reeb graph arc for both the boundary approach and for the interior approach. The extracted Reeb graph arc for both the boundary and the interior approach is smoothed through iterative refinement. In the iterative refinement process, once the initial path is identified, a new set of candidate points is selected at finer granularity in the neighborhood of the initial path to extract a new smoother path. The process is done one more time for further smoothing. Combining all the Reeb graph arcs, we can formulate the complete Reeb graph of that model for both boundary approach and for the interior approach. Now, we will present the improved results of GASP over the geometric barycenter algorithm, implemented in the state-of-the-practice TTK, for Reeb graph visualization. For the first property, arcs confined to the model, GASP outperforms the geometric barycenter algorithm by confining the arcs within the model. The improvement can be understood by observing the arcs, highlighted in red, which are outside the model, generated by the geometric barycenter algorithm. On the other hand, GASP successfully constrained all the arcs, including the red highlighted arcs, well within the boundary of the model. For the second property, compact arcs of the Reeb graph, GASP generates shorter arcs than the geometric barycenter algorithm. The improvement can be understood on the highlighted red arcs, which take a shorter path with GASP. For the third property, following the function gradient, GASP Reeb graph arcs align better with the gradient of the function than the geometric barycenter algorithm. In this case, the direction of the function is horizontal. Some of the geometric barycenter algorithm's arcs, highlighted in red, are nearly orthogonal to the gradient. On the other hand, the corresponding highlighted arcs of GASP align well with the function gradient. Thank you for watching.